Hey there. It's been a while. I've been busy. I built most of a compiler in the meantime. This is a project I've been working on for a year and a half now. I haven't been able to dedicate much time to it because for the past 14 months, I've been holding a full-time job. And when you spend most of your time working on software development for work, you don't really want to spend your free time doing it either. However, I have still been getting some amount of work done on it, and I'd like to show it off because I don't know, it's been a while. I find this stuff interesting, and this is my way to just talk into the void about stuff I'm interested in. So, middle pane here, I have basic write-up of where I'm at right now with my compiler project. So you can pause that and read that. We'll go through this stuff, but I want to give you like all the interesting bits up front. I've been not able to really work on my previous project, which is a Vulkan game engine, because I'm stuck on a Mac for work, and that's not exactly ideal for working on a Vulkan game engine. There are a few problems there. But I was working on this before that anyway, and the whole plan with this project is to write my personal projects in this language. So I'd be porting that code anyway, so yeah, I'm still indirectly working on it. Yeah, I should probably just get started. Here's a bit of a file, the example file. I can run it if I do that. It spits out a whole bunch of C code and then it runs it. This is actually the standard output being printed by the program. We'll get to that in a moment. This project isn't very big. It's less than 6,000 lines of code. But I spent a lot of time on it. I've spent a lot of time on the type system in particular because this has a fully generic type system with all of the difficulties that come about with that. Let me show you some generics. This is if you saw earlier, I can run test suite. I have a folder with a bunch of tests in it, and each test has a file, and it may or may not have an expect file, which has errors. And it builds each project and runs it and assumes that it runs correctly, or if it has expected errors, that the errors match the expected errors, so I can test that things generate the errors you expect. But this is the test case for the generic system. They're all pretty bare bones. I just implemented it a few weeks ago. And this is a weekend project, so yeah. I have generic functions, I have generic structs, and most difficultly I have, this is not the test case I wanted inner function. Yes. I have this spaghetti. This is something that the Rust compiler actually rejects, which is fun. Having functions inside generic functions that then use the type parameters of the parent function. The Rust compiler, quite rightfully, honestly, rejects this. They have to handle it anyway for closures, and I'm planning on handling it for closures, so I decided why not go all the way, because I'm planning on desugaring closures down into just local inner functions anyway. So yeah, we have this thing here. If I copy this into this file, I run that, it's just built and ran that. And if I make some edits, like swap these arguments around, we get errors. Woo! And they're useful errors. We got all sorts of stuff in here. The approach I took with this project was start with the hard stuff and then work to the easy stuff. So this doesn't have control flow yet, but it has a full generic type system and a whole bunch of complex const folding system and imports and modules and the beginning of standard library and extern functions and all sorts of crazy shenanigans. pointers and slices and all sorts of stuff. Doesn't have control flow yet. I started with the hard stuff. And building a generic type system genuinely is very difficult. So let's go through some of the things we got going on in this file. This is the example file that printed out Hello World in 42. You can see down here. We start off with an import. We are also importing from within that project. So there's this other file here that it's importing stuff from. All of the syntax is to be determined. I'm going to close that. All of the syntax is like to be determined. How it evolves over time, we'll see. So I'm importing from the standard library a module called standard out, these 3 items, which I use down here. Imports work as normal. I can also come down here, and if I remove print string from here, so if I come over here and go boop, so print string is no longer imported. It says like no symbol print string in current scope. When I come over here and I go fay standard out, and I fully qualify it, now it works. Unfortunately, I can't go over here and go import fay stood out, and then come down here and have just stood out print string. That doesn't work yet. I'll do it eventually, but that is the one thing that doesn't work yet. And none of these imports are relative. Currently, they're all relative to the root, which I'm fine with for now. I haven't made up my mind on how I want to handle relative imports, if I want to have them in the language at all. So that I'm not handling it yet. So they're all relative to the root. They're all absolute. Whether it be the absolute of root of the project itself or the standard library. As this is relative to the project root, this is relative to the standard library. We have some generic functions here. This is the general syntax. That's how you define multiple generics. I'm going to have to figure out how to shove generic balance in there some way. Probably going to end up being something like this, and then like print, and then generic b add. I don't know. Something like that, probably. We'll see. But yeah, that defines a generic type parameter that you can pass a type argument to, and it exists within this function. And you can call other generic functions from within there, passing in that thing, and it'll spit out some garbage C code, properly desugaring all of the different specializations out into their unique copies, and resolving to the correct one when it's generating the C code. And that's fairly well separated between the actual type system and all the details of the C generation. There's a little bit of interconnectivity just because with C generation, you kind of need to know what order to do things in, so you need a little bit more information about the order things reference each other in than you would normally need. So this type system does a little bit more state tracking than it might otherwise need to, but it's fairly cleanly separated. I'm going to plan on writing a bytecode interpreter with code reloading and backwards time travel debugging, which I'm really looking forward to using. That'll just be a separate code gen, and at some point I'll have to build a LLVM backend, or very likely write my own. I've already started experimenting with what it would take to start JITting, which is cool. I have a bit of a test project with that. We'll see. We have constants. If you'll notice here, they don't have a type annotation on them. They can infer the type of the constant from the expression. This is pretty limited. Actually, if I try to stick like a const, the struct equals my type A is 42 and B is 55.0. I can just say 55. I'm pretty sure that'll blow up. Yeah. So it's not perfect yet, but this is a type of expression that needs to be disallowed right now. I have plans in the future for handling that, but yeah. Showing my work. not fully complete yet, but it can type infer. And what's interesting is that this A doesn't actually have a type here. This greeting has a type of string, which actually it has a type of slice of U8. That's the slice syntax in this language. I always found Rust's ampersand syntax for slices a little bit weird. Like, I know the mental model behind them. I kind of have to at this point. I've been writing Rust for about 3 years. But I always found it a little bit odd. And if it's, like, you want to mutate the items being sliced, that's how you do it. That's the syntax. But this doesn't, so this has a type. But this one doesn't because it's a constant numeric. And it kind of has a type, but it kind of doesn't. It's kind of more of an implementation detail than anything else. I completely stole this idea from various other languages. I saw it in Odin, but I know they stole it from somewhere else. Dang it, drinking my water. A doesn't have actually a type here. It's just known as the compiler knows that it has a value, which is a untyped constant integer. If I had turned it into a decimal, it would be a untyped constant decimal. That's where the kind of type is, because it's either a decimal or an integer. Because they have different representations of the hood. I could be using like a big decimal implementation here and then have them all be the same, but that didn't seem worth it at the time. I'll probably do that at some point down the road when I've self-hosted the compiler, but I'm not going to bother right now. But the advantages of this is that the type system is built to be able to support types that infer into each other, and you're not really going to do that a lot for normal types, but for numerics, if you look here, this type A here, this field A is an I32. I just wrote a 5. That 5 is an untyped constant integer, and it coerces itself to be an I32 in this case. And same thing here with this 6 coerces itself to be an F64. This means that if I come down here to, let's say, let number equal 5, and let's just get rid of all of this. We have number 5, and I run that. Yeah, it's going to yell at me because it didn't infer that to coerce that to a type, so I have to give that a type, actually. Let's say I16, just so it's a little bit interesting. Yes, we generated that right there. It's a bit inefficient, the code gen right now, but it's like very simplistic code gen, the way it like separates out sub-expressions, which does mean I can guarantee the order of execution for sub-expressions, which is something C does not. So even though I'm compiling down to C, I can still like avoid that. But let's say I do like 5 plus 8, and I go here and we get 13 because I'm doing constant folding. And if I have like, let's swap that out for A plus 9. What would that be? Actually, let's say A plus 2. That'd be 10. Yep. And if I come over here and I say, let's say this is a U8, and I say A minus 16, and so that would be like minus 8. It's going to yell at us. It is going to yell at us. Constant integer -8 is negative, and so cannot be represented as a U8. I got all sorts of these sorts of things. If this was a float, A would then get coerced into that. This is not a float, it's a decimal, because they're both just untyped numerics at this point. A gets coerced into a decimal here, so they're both untyped decimals, and then it has to coerce to an actual runtime type, and it can't, because you can't turn a decimal into a U8. What is cool is if I come over and I go like F32, and then I go, was it 3.5? No, it was at 3.4? Yeah. Constant decimal 3.4 cannot be represented as an F32 without a loss in precision. I went all out with this. Like, there's a full frickin' system under the hood here, which I'm quite proud of. And I can, of course, say, like, plus A, And it works, because even though this is like an integer, right, it coerces and it just works the way you expect it to, right? So now I get 11.4, because it worked. But I can also come down here and I can say, let other number, we'll say, you'll say U8 again, equals A times 55. We'll get both errors. 440 is too large to be represented as a U8. And so this A here is both being a decimal and an integer, because it just coerces itself correctly. Everything just works. All of the integer math, the compile integer math, is being done on a I-128, which gives me enough headroom that like I don't have to worry about anything. Unfortunately, that sort of stuff doesn't exist for floats, so all the decimal math is being done on an F64. Implementation detail could potentially lead to a bit of loss of precision, potentially, but you're dealing with floats. At that point, you're going to have all sorts of precision issues anyway. So, and you can't represent a number, a float larger than F64 in the language itself anyway. So, like, in order to coerce, even if you could represent a more precise value, you would still get that, like, loss in precision error to try to assign it to anything in the actual program, because you physically can't represent a value that precise in the language. So, it's fine. It'd be nice to unify them so it makes the system a little bit simpler. So it'd just be like one big decimal type. So if you notice here, I've been using this let. If I do that, this let here, let me go back to 5. I'll say, yeah, plus A. So we have that. And if I try to mutate that, number equals 5. And I can just assign 5 to it. It'll be 5.0, because it just works. Numbers just work. But you cannot assign to a mutable binding number, because it's not mutable. So let's make that mutable. And now I can assign to it. And you can see here it assigns 11.5 and then it assigns 5. And then I can print that out. So if I go up here, print F32, F32. Print F32 number, and we'll see that thing. And of course, this is whatever the hell the libc of my system decides to format an F64 as. Let's do print new line. There we go. If we jump into that, there's no currently any warnings about like unused imports or unused variables. That'd be pretty easy to do. Just haven't done it yet. If I jump into std_out here, we can look at extern functions. Externs are gross, but you kind of have to have them. You have to have some sort of way to like call out to the outside. And because I'm running in running via C generation, you kind of have to play by C's rules. So you have to have this gross stuff of like, compiler, please emit an include statement for me. I'm planning on also having like include local, which would be like arrow brackets versus quotation marks, because they're both using quotation marks in the syntax, because it makes my parser simpler. But yeah, we have a whole bunch of printf aliases here because I don't have var args in the language, and having var args in the language, I don't want to do it in the same way that C does it, and that means I'd have to implement var args both the C way and the fey way, and with C var args you can't forward them to another function, so they're quite difficult to use for like wrapping around an extern function to like make your own printf. If you like don't care about compiler verification or anything, right? Like you're just like, let me just trust that the libc will do the correct thing with whatever I tell it. And which usually means you're going to tell it the wrong thing and it'll blow up, but that's printf. So I haven't done that. I haven't done that yet. So it's just basic extern. And because printf is a var function, you can just like lie to the compiler and it'll generate the correct thing. If you look here, like it goes down to the right thing. If you look here, we have this printf32 that we were calling. If we find that, here we go, printf32 takes an arg, and that's u32. I can't read f32. There we go. Arg of f32, and we print out, we have this specific alias for printf, because extern, you have to provide it the name of the symbol in C, and then your own symbol name for it, because I might have different symbol validness rules than C does. Because if you look, I am not generating actual symbols in C, right? Like, none of this makes any sense. I'm not planning on generating debug information in this copy of the code gen. So I'm not playing by C's rules here, and I don't want to play by the rules of any language that might have whatever their symbol format is. Whatever, like if they like support having this, like that could be a valid symbol name, I think. I'm not sure. I don't know. It probably depends on the executable format and the linker. Who knows? So you have to define that there, and then we specify what we call it inside fay, which is really useful for these sorts of situations where you have just like a whole bunch of aliases of the same thing. So we just tell the compiler, I lost again, we tell the compiler that there's a copy of it. It takes a format, just a pointer to U8, and an F32, and we like pass in the format thing for it. If you notice here, I actually have a null terminator manually inserted into this string. And then I pull out the pointer for the string, because the strings in fay are slices. If I go to print string up at the top, that's what a string looks like in fay currently, because it's just a slice of U8, and it has a pointer and a length. Pointer and a length, and you can dot call on there to get them. And so we gotta get the pointer out, but the format argument to printf needs there to be a null terminator. And technically all of the strings in this language have a null terminator, because they are, even though I put them into my own like slice structure that's generated by the compiler, I am still using like string literals in the C code. That's kind of undefined behavior, because other code gen might not do that. I'm doing that as like a simplicity, like I don't have to dump out big long arrays of hexadecimal to do string, because that's less efficient. So I'm just not. So technically the program would still work if I removed that, but undefined behavior. Don't love that, but that's a case of just one of the things that happens when you compile down to another language that has their own rules for stuff like that. Ugh. If I pull up, we have all sorts of string escape sequences. If I pull up here and I go print string and I go hello world, we say hello world, but then I can come over and I can put a new line. We get a new line. I can escape a pair of quotes. And I can also come in here and before this go boop boop. And so now we have that. If you wanted to do that, like that works. All of that works. And I can also come over here, and if I want to blow up, I can print a null terminator. No, I can't. Why can't I print it? That's funny. I'm using the length specifier for printf. I guess it still blows up if there's a null terminator. That's funny. Ugh. I'm going to eventually write my own printing mechanism. It's going to be part of the compiler, because I can't be bothered to design a language that like lets you build that in language that's in a reasonable way, because I feel like most of the languages that like are powerful enough or expressive enough or just like let you do enough weirdness to implement like a proper validating print function in language typically ends up with all sorts of weird oddities, or they're just too complicated for those reasons. So I'm not doing that. And also, because this language is just for me, it's fine if I hard code into the compiler a few features, because it's just for me. So, like, I don't need the language to be capable of that, because downstream users need to be able to implement their own thing. I own the compiler. I can just do what I want with it. And hell, languages like Rust still, if you use any sort of formatting utility in the same library in Rust, that's all compiler intrinsics. It all compiles down to compiler intrinsics, even though it's a macro at the language level. It's not actually implemented in the language. It's implemented in the compiler, so, like, that's fine. If I pull back up the README, we got modules, we got consts, we have bindings, block expressions. I haven't talked about block expressions. If I come over here and I say, well, first things first, I can just come over here and I can print string hi, and that'll work. And it will actually generate a scope for that. So things will go out of scope if I define a variable in here. But I can also come over here and I can say let a equals this. And it's going to yell at me right now. The compiler's going to yell at me. Cannot create binding of a void. Right now the compiler doesn't handle like multi-line spans for errors very well. I have that as a to-do list item. Actually, it's right here. But it falls over in the correct way, so it's fine. But yeah, so this is a block expression. It's perfectly valid to have it in expression location. It only ever evaluates to void currently, which means you can't actually compile any code with it in expression position, but it works. I need to have some sort of like give 5, and then you come over here and it's like this is an i32. Or yield is what Yact calls it. That doesn't exist yet. That's not a thing I do yet. Well, that's interesting. I wonder why I did that. Oh, because they're different. Actually, they're actually different things. Yeah. Because this was the error message where, if you notice, variables can be inferred of their type. If I say let a equals hi. I say that, and then I pass a into there, like that works. So variables can infer their type, and so that was the. There we go. Nope. This is the type error for when it's trying to infer to void, as opposed to it already knows what type it is, and it is void. Is that thing. Actually, if I come over here and I say void, I wonder if that will blow up. No, good. Good. I implemented that correctly then. I wasn't sure if that was gonna like crash the compiler or something. Yeah. If we wanted to like say create some, let's say we wanted to allocate some memory, we could like say c include system stdlib h, and then now we have access to malloc. We can say extern malloc fun c malloc. Yeah, I was going to use this to show off generics, but I just realized I don't have pointer casts yet, because that's one of the easy things to do that I just haven't done yet. Size, usize, and it returns a pointer to U8. It's a mutable pointer to U8. That's important. And extern free. Let's just call this malloc. Free fun free. Pointer. Let's call it putter. Mutable pointer to U8. It doesn't return anything, and we can come down here and we can get rid of that because that doesn't work, and we can say let putter equals malloc 1024 bytes. Sure, and we've run that, and somewhere in here, yeah, we malloc 1024 bytes. And we can also then say free putter, and we free that. So it ends up getting passed around a whole bunch, because the way that the codegen works, it's there for a reason. It can be a bit smarter. It already has smartness in a few places to be able to like avoid duplicating lines if it doesn't need to. Well, duplicating variables, I should say. The reason that this mutability actually needs to be there is if I do this, the C compiler is going to yell at me because error passing const u8 pointer to parameter of type of void discards qualifier, because the void pointer argument that free actually expects doesn't have const. I'm actually turning this this mutability information into actually like stuff on the C end, so that the C compiler can hopefully be a little bit smarter. They're not usually, because C programs tend to like not actually behave with regard to their constness that they themselves define, because it's not well checked in C as a language. It's better checked in C++, but it's not very well checked in C. But also, with all of the compiler errors that I have turned up, C codegen, a whole bunch of compiler errors, a whole bunch of things also that aren't useful to me. It is useful to at least have one more layer of defense between, oh no, I screwed up mutability somewhere, and not doing anything about it. So like having one more thing that can catch that sort of issue. Oh, parsing. Parsing's difficult. If I come over here and I type some garbage. Oh, this is actually a case where it actually handled it well. What's very difficult to build in compilers is it's very easy to just like throw up on the first error and exit, which is what my previous projects have all done. It's much more difficult to stop and say, okay, this is invalid. Let me go add it to the list of errors, and then try to get back into a sane state so I can continue checking the rest of the program. Be syntactically or semantically. Like if I come here and type some more gibberish here, we're going to get... Ah, that's funny. That's funny if I type some gibberish here. Oh, joy. You see, this is where the parser is managing to recover in a way that works, but isn't exactly what I was expecting it to do. Regardless, you have to get the compiler back into a state that it can check the rest of the program. So this is capable if I come up here and I type like here. There we go. That'll give us multiple parse errors. Multiple parse errors. So if a parse error occurs, it'll attempt to get back into a sane state. It doesn't always handle that very well. It's mostly a heuristic right now, but it's better than nothing. And it can continue to improve, because right now the parser isn't very aware of its own errors. But as it gets better about that, specific cases will be handled better, and it'll just overall become a lot nicer, which is kind of how you have to handle it anyway. However, the semantic checking is so much more interesting and so much better. If I generate some random garbage, so if I say like this is a decimal here, and then this is putter A, and I say this is putter B, and then I come over here and I say this doesn't close, and Ah, that's funny, because it actually did throw up fully. Unexpected end of file, because the string doesn't close. No buffer, no symbol B after. Where is that? Line 7? Oh, yeah, because this B after function doesn't exist because it's part of the string now. Haha, that's funny. And then missing main function because it wasn't able to close the main function. So there's no main function in this project right now. Let's reclose that. I was hoping that would be a fun syntax thing. All right, number is a float, right? I32, and this is 3 plus A, and then there we go. So, assignment type mismatch for this whole thing. Left type, it says this is the number, left type was I32 and the right is untyped decimal. These are notes. So an error can have like multiple steps to it. And then we also have here a validation error because this doesn't exist because I changed the name. And if you notice, they're both validation errors. They're both like a few lines apart, and the compiler just like handles it. And that's quite easy to do. What's really interesting if I get rid of that, and then I call this putter, and then I call this putter, so we're back in a building state. We're in a back in a building state. Cool. If I create a function, I call it fun my func. If I can type, that would be glorious. And I say this returns an I32, and I return some gibberish. What would you expect this to do? It's going to attempt to parse this as an expression because it comes after a return statement. It's going to assume that's probably a variable name. So it's going to pass parsing. This is syntactically valid. However, once it gets to the semantic step, it's going to say there ain't no variable named this. Complete keyboard throw up. This keyboard vomit. Anywhere in the scope. I don't know what it should be. I don't know what type it should be. I don't know if it's anything about it. And so previously, the compiler would then fail to validate the return statement because it's like a requirement that the return statement needs to actually handle, like in order to know the type of the return statement, to check that the return is of the correct type for the function, you need to know the type of the expression, and it didn't know that, so it bailed, and so the return would never get checked, and so then you would get an error that this function never returns, because in the semantic tree, which is what is at the end, and is also what the code gen operates on, their return statement just wouldn't exist. However, if I run this, we only get the one error. We only get the error that variable doesn't exist, because when that sub-expression gets validated and it fails to find the symbol, instead it returns back out an expression of type any collapse. I was trying to remember, my brain was saying like any coerce, that wasn't it, it's any collapse. Silly dumb name, but it collapses, which is the internal name for a coercion, it collapses to anything. So even though it doesn't know what this is, it throws up its hands, it generates an error, it then tells its parent, hey, I got an expression for you. And it gives an expression that can affect, in semantic terms, evaluate to any value under the sun of any type that it needs to. And because the type system is built to handle this sort of coercion for numbers, specifically numbers, this just works. It's a type that can coerce to any other type. This is a very strongly typed language. I'm not intending to have anything else, but this is really cool because the return still gets its expression, and then when it needs to double check that its expression is of the correct type, it says, hey, does this I32 and this any collapse match? And then the any collapse goes, oh yeah, I'm definitely an I32, and it works. And it works. It's so wonderful. I can come over here and say +4. And and it'll crash in the constant folding for some reason. No, that's not constant folding. That is coercion. Collapsing from integer with a non. Oh, That's funny. So it's trying to collapse into an untyped integer. And so then it can't actually do that because it's not actually an untyped integer. So this is the coercion and the constant folding fighting. That's really funny. If I said like returns int, and I had a function here, fun returns int, it returns an i32, and then I have a return 5 or 4, sure. That'll do what I expect. That's one for the to-do list. To do. Don't allow any collapse to an untyped numeric. Cool. Yeah. And also, of course, it goes without saying that with all of this, if you can tell, it doesn't matter what order symbols are in for like functions and types and stuff like that. It just handles it, and then it generates the code that's correct for that. Also, if you notice, I'm not calling this function, but yet the body still gets validated. Take that. That's a dumb statement. Yeah. If I can get rid of that. I need to do a whole bunch more warning stuff. There is a few places in the compiler that can generate warnings that are non-fatal to the compilation overall. I'm going to continue adding more stuff like unused imports, unused variables, unused functions, all sorts of stuff. I need to add, if I pull it back up the README, I have the README right here. I need to do control flow. I haven't done this yet because I need to, it's part of like how the expression validation happens. Because I need to be able to track pretty precisely the control flow for enums, because enums in this language are going to be flow typed, where you think of them like unions in TypeScript, where if the flow control dictates that you can't get to a certain point without having already disproven that an enum can be of a specific variant, then that variant is removed from the type signature of the value at that point in the execution. That's a very dumb way of saying, if you can prove to the compiler that a value that's an enum can't be a specific variant, it can't be that variant. And so you can do stuff like, let's say, am I in a building state? I'm in the building state. Cool. If I have a function, how am I going to show this? If I have a function called does something, and it returns an option of, let's say, U64, and because I want this to actually build for now, I'm going to actually define an option type, even though it's not going to do anything. Option is going to be generic over T. It's not going to have any fields. That'll build. Not all code pass for function does something, returns value. Thank you. So if we have this does something and we return option. Yeah. I need to be able to infer. That was a complete keyboard mess up. I need to be able to infer stuff like this in more places. And it yells at me because it's an empty struct. Whatever. I don't fucking care. Extra field. What? Unexpected extra field initializer. I've been creating. What? Do I not construct? I definitely construct generic structures above. Yeah, I definitely construct generic structures all over the place. I don't frickin' know. I'll need to look into that. Anyway, regardless, let's pretend that this builds. I was trying to do something that is dumb. Returns an option. Why not? Sure. But then we have we're down here where let value equals does something. And then we can say is if value is none, return. And then now here value is known to be some, and you can just use the value. In Rust, this would look like it'd be let some value equals does something else, return. That's how it would look in Rust. And the problem with this is that this is really nice. I'm really glad that this exists in language now. I'm so glad that Rust format can actually handle it now. I'm glad that they're not going to ship anything without Rust format support anymore. That was a fun shenanigans. The problem here is that if it, let's say it's not an option, let's say it's some other richer enum with some other value. Let's say it's an error value, and let's say this is okay, right? And here you want to be able to access the error, right? You want to be able to access that. You can't do that with this construct in Rust. Here, if value is error, and then I can like print error, return, and you can do it, and you still know that value is okay down here. You can just use it. Again, one of the reasons why coercion is in language is that, like, if it's, it's a value that, like, is if it's a single enum variant with a single item in it, you can just treat it like the item. That's one of the things I'm planning on trying out. We'll see. We'll find out. So I gotta do some pattern matching stuff. Looking forward to that. Not really. Gotta do methods. Gotta do visibility modifiers. So once control flow, pointer casts, pointer dereferences, methods, and visibility modifiers are done, which all of those are like not very big. All of a sudden now I can start implementing type safe containers. Woo! That's fun. This is like half an hour of work I need to do at some point, so that you don't have to like specify the this every time. Like, so like arg here is known to be a t, so it doesn't need to pass t in here. It should just be able to infer that from the argument. That's easy to do. I just need to do it. Traits are going to be a bit more difficult, mostly because I'm not sure of the syntax I want to do, because the method syntax is going to be slightly different than most languages. So the trait syntax needs to be different to match it. Like, it has to make sense in context. Generic bounds are fine. The type system, the generic type system is already written such a way that, like, once I have trait bounds, I can pretty easily make it so you can, like, call and access stuff on the generics that have the trait bound. That won't be too difficult. Anonymous structs, because I like returning lots of things and I don't like tuples, and anonymous structs is the correct solution. Enums, that's going to be difficult, tricky. The flow control is the difficult part. I gotta make the parse errors continue to be better, because at that point I'm starting to get at that point in like the to-do list, I'm starting to get into like I'm genuinely trying to use this for stuff now. So this is just like make it a little bit better, humanize it. I need to parallelize it. The compiler was designed from the ground up to be fairly parallel friendly. Not everything can be the generic type system, because ideally you would want to parse all the files in parallel. So you have n number of workers, and they steal out of the the pool of files to, I think work steal is not the right term here, but they all pull from the pile of files and they parse them. And then ideally you want to be able to just go through, and this is how the compiler was originally designed. You want to just be able to like walk through the root level of all of the files to pick up all of the public symbols, populate those into all your like type system and your symbols and stuff like that. And then you should be able to like validate all of the files in parallel without touching each other. And if it wasn't for generics, that'd be true. However, generics, because you call a generic function with a certain type argument, you need to know which version of that function that call is for. So you need to know the correct specialization. And those specialization IDs have to match up between files for like the whole project to build correctly. Well, actually, technically it doesn't, but you'd have to generate like a lot more code. Because you have to generate separate copies of everything for each file, which is ugh. So there has to be some amount of thread synchronization there. I have some interesting ideas for how to avoid contention and to do some caching around that, which should be nice. The whole thing's pretty well structured for, it's mostly just type system stuff. Code formatter, I've done one of these before. It's a simple syntax. This is the point at which I'm going to start being like a bit more solid about the syntax. You do tree sitter grammar because the editor I use uses tree sitter. And while it doesn't have the support to load custom grammars yet, getting there. It'll get there eventually, and hopefully by that point I can do that. Because like I don't really care about code highlighting, but I do care about like having the editor know about the semantics for like auto indent and stuff like that. And then I need to start working on a language server protocol, which again, the editor I'm using doesn't really like support custom servers yet. I work for the company building the editor. We're working on it. Yeah, so I'm really excited about this. I've been working on this for a long time, and I've kind of taken the approach of don't show what you haven't built yet, because when you're a dumb kid on the internet building something what you think is cool, it's really easy to get in this mindset of like everyone should be excited about what I'm working on, which isn't true. Not even remotely. No one gives a shit, right? And so I've just been working on this. I think this is interesting. I think this is a really cool spot. I spent a lot of work on this type system. Oh my god. I got a lot of things working. I'm getting close to start being able to write some real programs with it, which is really cool. It's the closest I've ever gotten to that with any language I've built. And yeah, I'm really excited about just using it. I have a bunch of error handling ideas for like program errors, not compiler errors, but like program errors. Which is one of the big reasons why I wanted to write my own language. There's a whole bunch of other little things that I want to do better than Rust. It is, unfortunately, an unsafe language, which is kind of one of those things that, like, you have to do it better than Rust to bother doing it. And I don't think that I could build, right now, I don't think I could build a borrow checker that's better than Rust's, because my brain is used to Rust's borrow checker, and the rules are so deeply ingrained in my brain at this point, I would just end up poorly recreating the Rust borrow checker. In order to build a borrow checker, I'd need to do something unique and different that has different trade-offs, and I haven't come up with anything, so I'm not going to. That is a downside of building your own language, is that I'm one of those people who's drunk the Rust Kool-Aid and is like, yeah, memory safety is important, lifetimes are important, that sort of stuff. And so this language is kind of a gamble of, are all of the other things that I feel like I can do better for my specific tastes worth what you're getting up by not using Rust? I think so, especially for the type of programs I want to use this for. Lots of low-level game engine programming, that sort of stuff. And I feel like I can make a better experience for those sorts of things that I care about for those sorts of tasks. But it is still a gamble. Because I might get through all this and decide, no, it's not really worth it, and then have to turn around and redesign the language to be able to host a borrow checker, because you have to design that sort of stuff into the semantics itself. You can't just like bolt it on. We'll find out. We'll find out. It's fun. This is why we do these sorts of things. It's cool. Anyway, yeah. Yeah. Well, talk to y'all later. Cheers.